and control of digital assets. We bring together stakeholders to collaboratively develop interoperable infrastructure. We design decentralized solutions where everyone wins, and we are a neutral not-for-profit to enable people to control their digital destiny. We wouldn't be able to be here without our sponsors. Thank you very much, all of these organizations, for contributing to our stack and our work. If you're interested in becoming a sponsor, please contact me directly or mail us at team@blockchaincommons.com. Today's topic, we're going to be talking about Exodus protocols and then a deeper dive into Hubert, which is a dead drop hub. So last month, we introduced clubs, which are autonomous cryptographic objects that allow information to be transmitted, updated without traditional infrastructure. And as such, they support coordination and collaboration. And the reason why I'm bringing this up particularly today is that it is an example of an Exodus protocol. So we're going to be talking about that later in the presentation. But if you want more about the Gordian clubs, our developer website has more details. So Exodus protocol, what is it? It's infrastructure that can't be revoked and that survives when platforms disappear. And as such, they're built on mathematics instead of permission. So what is the problem we're trying to solve? We're fighting against infrastructure that disappears. Everybody has experience with emails, photos, MP3s, various kinds of services, communities, et cetera, where the infrastructure just disappears. And in some cases, the disappearance is purposeful. In the case of financial censorship is a classic example. Everyone has their own story of loss by this point, and we're not really seeing sufficient solutions to this. So what is an example of an Exodus protocol? Well, Bitcoin. Miners come and go. Anyone can spin up their own node. You can create your transactions offline. You can transmit via QR codes or Blockstream satellite, and you can send when and where you want. This means that Bitcoin proved something profound, that basically fundamental capabilities can exist as mathematical rights rather than as some centralized privilege. Because when your ability to transact depends on a bank's approval, it's not a right, it's a permission. Bitcoin made value transfer a right. And so for 15 years now, it has demonstrated autonomous infrastructure that works. There are no servers to shut down, no administrators to pressure, no companies whose failure really matters. But Bitcoin is a single use case. Bitcoin supports value transfer on the internet, but we want to do other things. We want to support coordination, collaboration, identity. Our club's concept is just a first step in that direction, but I believe we're going to need many more Exodus protocols. Now, Exodus protocols are not for all use cases. Sometimes centralization is very useful, when you're trying to protect grandma against scammers, when you're trying to protect your children, et cetera. Some measure of centralization, some level of support is needed. But I believe underneath all of these, we need to be able to go to a strong foundation in the form of an Exodus protocol. So we've identified 5 patterns for Exodus protocols. We want to be able to operate without external dependencies. We want to encode rules in mathematics, not in policy. We want the constraints to actually be load-bearing. We want to preserve exit through portability, and we want to work offline and across time. So I'm going to talk a little bit more about these. Pattern 1, operating without external dependencies. Basically, if it requires permission to operate, then it's not autonomous. So the more general pattern is self-contained cryptographic objects that can function without asking permission. Now, Bitcoin's approach to this is distributed verification across thousands of independent nodes, no central server, no phone home behaviors. The sum of this is this pattern helps us create coercion-resistant architectures. Pattern number two is we encode rules in mathematics, not policy. The principle, math doesn't discriminate, does not take sides, doesn't change its mind under pressure. And a particular approach to that is cryptographic proofs replace administrative decision making. The verification is deterministic. And of course, the obvious example from Bitcoin is that consensus rules in protocol code resulting from the cryptographic proofs, not from any administrator's decision. Leading us to the concept that code can be coerced, policy can be coerced, but mathematics cannot. Pattern three, make constraints load-bearing. What can't be changed can't be weaponized. Oftentimes, what appears to be a limitation can actually be a freedom. A limitation of can't expire also means it works forever. A limitation that it can't phone home means perfect privacy. In Bitcoin's example, each limitation protects us against capture. You can't reverse a transaction as a limitation, but that also means that we have this strong capability because funds can't be seized by fiat. This is fundamental to coercion-resistant design. Pattern four, preserve exit through portability. Now, the principle is that lock-in is the opposite of sovereignty. Exit is not an escape, it's leverage. So the general pattern is interoperability and open standards, no proprietary formats that trap users. If you think about this from the terms of Bitcoin, your keys work in any wallet, and the open protocol means the freedom to switch implementations. You can take your seeds from one wallet to another wallet to another wallet and use the one that works best for you. Without the ability to walk away, consent collapses into coercion. So this is an essential Exodus protocol pattern. Our last pattern is working across time and working offline. The principle is that infrastructure that requires connectivity can be denied that connectivity. So that means our pattern is we want asynchronous operations, we want things that work during outages, and we want things that survive across decades. Bitcoin's approach, well, we can sign transactions offline, we can broadcast them later. The protocol doesn't fundamentally require connectivity at all times. Thus, the true autonomy of Bitcoin works when coercion's attempts to deny it fail. But obviously, autonomous systems like clubs can use these principles to implement these patterns to coordinate. They can do threshold signature ceremonies, they can do governance decisions, they can do access updates, they can do capability delegation without requiring servers, because servers, create a centralization and then an opportunity to denial. So how do we enable communications without breaking the patterns? Well, one answer we have is Hubert, which is a dead drop protocol, which we're going to be talking about in a minute. It basically allows for coordination via dead drops. So meet Hubert. It is a dead drop hub. It is a hub of BERTs. We'll talk a little bit later about what that means. It is a distributed infrastructure for secure multi-party transactions. It enables coordination without servers or intermediaries. It is completely opaque to network observers, and it's built on write once distributed storage and cryptographic addressing. Now, in order to understand this, you have to have a little bit of understanding of our underlying technologies, in particular, Gordian envelope, which are smart documents with encryption and progressive disclosure. One of its fundamental capabilities is it allows you to reveal things in layers because we can elide information. We can basically selectively redact portions of it until those portions are required by the receiver. And all of this is done through self-contained cryptographic proofs. Within the Gordian stack, we have ARIDs, which are apparently random identifiers. We can use these as capabilities to enable cryptographic write-once storage or derive storage keys. And in general, ARIDs are never exposed publicly. They're only shared via secure channels. But the possession of an ARID allows for read access or in case of some of them, write access. The result of this in Hubert is messages are opaque to networks but transparent to recipients. Um, that's really the essence of Hubert. But another Gordian stack technology allows us to do coordination with authentication and encryption of messages, which is GSTP, our Gordian Seal Transaction Protocol. It's built on envelopes and it supports sender authentication and receiver encryption, multi-recipient capable with encrypted state continuations. Networks only see the encrypted envelopes and it has complete metadata protection. GSTP is also used by Foundation Devices' most recent hardware that basically protects everything between the trusted chip on the device and the trust zone on, say, an iPhone or Android. Everything between is sealed in the Gordian Seal Transport Protocol. So this is being used in real products. So how does Hubert implement these exodus patterns? Well, it has no external dependencies. We're using distributed storage, DHTs, IPFS. It's mathematics, not policy. We use cryptographic addressing through ARIDs. All of the constraints of it are load bearing. It's write once, which means that we have immutability. The portability preserves exit. It's an open protocol. There is no lock-in. And it works offline and across time because it supports asynchronous coordination. An example of this is a frost ceremony where we want to have, say, a 3 of 5 threshold signature. The coordinator publishes encrypted signing requests with responses for other ARIDs. The participants can retrieve the requests from the DHTs or IPFS. Each party generates their signature shares and publishes those encrypted at the coordinator's ARID, and then the coordinator can receive the shares and complete the signature. The network observers only see the encrypted envelopes, and there is really no server that coordinated this ceremony. They're all using dead drops. So what does Hubert enable beyond Frost? Well, our use cases are journalists to protect sources with distributed storage, activists to coordinate during network disruption, immigrants with credentials that don't phone home, disaster response teams working where infrastructure has failed, and privacy-focused communities that are organizing without metadata exposure. With Hubert, they can do this all without servers, all without surveillance. Right now, we have 4 options for the storage backend. There's the BitTorrent mainline DHT, which is fast and lightweight, but is also very small. IPFS allows for larger capacity. We can do hybrid with automatic size optimization to use both. And then we also can do a traditional server environment for testing and controlled deployments. But all of these use write once semantics, which eliminates race conditions, preserves immutability, and no one can modify or delete a published message. There is a bit of lineage on this. Ted Nelson's Xanadu project had this concept of a BERT, which was named after Bertrand Russell for a variety of reasons. They had something there themselves called a club system, which was an early capability-based security. Very early, this was late 1980s, but it was a vision for decentralized coordination of the ability to interact with objects. Mark Miller, in years since, has refined capability security models since then and offered object capabilities in the E language. This brings us to Hubert today, a hub of BERTs, where autonomous objects can coordinate and cryptography finishes what Xanadu started but was unable to finish. So now we're going to do a technical deep dive. Wolf will demonstrate ARID generation, some storage backend operations, bidirectional coordination flows, and how the CLI and API works. So we're going to see the code for the community, 0.1 version, and the GitHub for this is Blockchain Commons Hubert-Rust. Wolf, do you want to take over?
Great. Thank you, Christopher. Let me share my window here. You should be now seeing my slides. I have a few slides to go before I actually go into the CLI-based demo of the Hubert tool. Uh,
Okay, do introduce yourself.
yeah, I'm Wolf McNally. I'm the lead researcher for Blockchain Commons. And in this session, I'll be demonstrating Hubert, which is our distributed coordination protocol. I call it a protocol, not a server, even though it can be supported by servers. And you'll see why as we move forward here. Um, Okay, so first, Hubert is a protocol that facilitates secure multi-party transactions. And I will be reiterating a few of the points that Christopher made, but we'll be going to a deeper dive here as well. So the principles are that participants write once using random keys to essentially a large key value store. And the messages themselves that you write contain random keys for expected responses, enabling bidirectional communication. To third-party observers, there's complete opacity to outsiders through end-to-end encryption. There's no central server required for coordination, and there's trustless operation using public distributed networks. So a few of the technologies that we'll be touching on here, we have other presentations that go into these in much more depth, but I wanted to kind of mention them here in case you're not familiar with them, that you'll at least understand what you're seeing is other parts of our stack that we're building on. The first one is the uniform resource, or UR. You can think of that as similar to a URI or a URL, but it's a self-contained binary object encoded as a URI. It's defined in one of our Blockchain Commons research documents, and you can find all of them at our research repository, at our Blockchain Commons /research repo. It encodes binary data as typed, easy to handle text URI. And its general form is UR colon, that's the scheme, and then a type string followed by a slash, and then a series of letters that are called byte words, or they're basically 2 letters per byte. So it's not as efficient as, for example, base 64, but that's not the point of URs. They're designed to be much easier to handle in many other ways. So again, I'm not going to go into the details here, but when you see things with UR colon, you'll understand that's what we're doing. We're encoding self-contained binary objects. The second is the ARID, which Christopher mentioned. An ARID stands for apparently random identifier. This is defined in another of one of our Blockchain Commons research documents. Again, here's the URL. An ARID is 256 statistically random bits, or 32 bytes. And they can refer to anything, but they can't be correlated to anything. And that's one of the basic ideas of ARIDs. Even unlike, say, UUIDs, which these are actually longer than UUIDs, but UUIDs also often contain bits like version numbers and so on. ARIDs are completely statistically random, which means they can be derived from other sources and they can contribute to other sources without loss of entropy. So in Hubert, ARIDs are addresses of cryptographic dead drops, and you can think of them that way, and you'll see how we apply them in the coming slides and demo. Just want to talk a little bit about what a dead drop is. A dead drop is, the term is from Spycraft. It's a way to exchange messages where the parties never have to meet in person. And so 2 examples you see here is a spike that can be driven into the ground. It has a capsule and a leather strap at the end that can be used to pull the spike out of the ground, or even something as common as a bowl of walnuts where a one-time pad script can be put inside it. The sender leaves messages at a known location, and the receiver visits later and picks it up. And that's basically the operating principle of Hubert. This does require out-of-band coordination to set up locations, protocols, and signals between the participants. So, for instance, when you leave a dead drop, you have to make sure that the person who's going to pick it up knows where to look for it to pick it up and knows what form it's going to take. And those things have to be coordinated out of band. And this could be in the case of an initial ARID to kick off an exchange like a Frost signing ceremony, something like that, could be exchanged via copy and pasted signal. And that's part of what URs are for, is to make these kinds of binary objects easy to handle in situations like that. So the next technology we're building on is Gordian envelope. We have extensive documentation and presentations on YouTube and elsewhere about Gordian envelopes. So I'm just going to touch on a few of the kind of highlights here. They're a smart document format for structured data with a built-in Merkle-like digest tree. Their core superpower is they support hash data elision, which could be considered to be selective redaction. And by elision, I mean you can remove the data, or you can encrypt it, or you can compress it with verifiable inclusion proofs. And we support progressive disclosure, which means you disclose only what's needed while signatures remain valid. And that's actually a pretty remarkable thing. Nothing else that I'm aware of does that. At least not does it in the kind of radically recursive way that we do, where envelopes can contain other envelopes. It's envelopes all the way down. Our design is privacy and human rights oriented, and so we basically support kind of the best practices in the privacy and human rights domain. Um, we support flexible cryptography. We support Schnorr, that's our basic signing algorithm, but we also support ED 255.9, SSH signing. We have several algorithms for encryption. I don't mention it here, but X255.9 and post quantum algorithms like MLChem and MLDSA that we've discussed in other meetings. But we have full support for various kinds of signing and encryption. We support non-correlation via SALT, and I've discussed what that means elsewhere, but I'll mention it here again. It's well suited to storing and conveying cryptographic seeds, keys, verifiable credentials, and other high integrity artifacts. It's a very compact binary format with minimal overhead, and it's wire agnostic. Integrity, privacy, and semantics travel with the data, and therefore it's ideal for offline or air-gapped and multi-hop workflows. And finally, built on top of that, we have the Gordian sealed transaction protocol. This is built on top of envelope, but it's a way of using envelopes where we support secure transport agnostic request response and also event broadcast protocols built on Gordian envelope. You can work it over HTTP or TCP or Bluetooth or NFC or even QR codes, SneakerNet, Tor, etc., because it builds it in its own security, so it doesn't matter if you use insecure channels. Messages are both encrypted to recipients and signed by the sender. And we also provide what's called encrypted state communications, which is the idea that you encrypt something back to yourself to be returned to yourself later by a responder to a request. And that way you don't even have to store your state locally. It comes back to you encrypted, only you can decrypt it, and then you can continue the workflow from there. And since you know you sent it to yourself, it's self-signed and self-encrypted, you can trust it. We support asynchronous and peer-to-peer friendly protocols, but we also support classic client-server flows and multimodal or multi-channel transactions where you can move back and forth between different channels. You can start with a QR code and then continue it in Tor. We also, as a matter of kind of best practices, we encourage idempotent actions, so retries over flaky links are safe, and we're designed to be wire agnostic. Okay, so now on to the storage layers of Hubert. We support three basic storage layers, the two that would be mostly used in production and distributed uses, and one that can be used for local area networks, that's a SQLite. I'll discuss each of these briefly before we go into the demo. So first, BitTorrent. BitTorrent uses what's called the mainline DHT, or distributed hash table. It's used by BitTorrent clients to find peers without central coordination. As of 2013, which is some of the most recent data I could actually find, and BitTorrent has only grown since then, the current number of users of mainline DHT was about 16 to 28 million, with intraday changes in the DHT of at least 10 million. It's a UDP overlay where peers collectively replace trackers. Keys live in a 160-bit space, and lookups walk closest nodes. It's a sloppy DHT, which means it's eventually consistent and best effort. Items expire without reannouncement. And it's to be used as a signaling and coordination layer, not durable storage, which is perfect for what Hubert used for, actually. It has two data modes. One is immutable items, where the key in the key value table is the SHA-1 of the value you're storing, and therefore is bound to the value. But it also supports mutable items, where the key is the SHA-1 of the publisher's ED25519 public key with optional salt. The values that you stored in DHT are practically capped at about 1 kilobyte. And you should expect messages to last about 30 to 45 minutes without republishing. In practice, it's often longer, but you should be conservative about your expectations. We use the mutable mode by stretching the ARID into an ED25519 key pair. And that's important because even though we're not mutating messages ever, we do actually need to have the key that's the value that's different from the key, and that's what enables that. So we derive the private key from the ARID deterministically using HKDF, and we use that private key for signing the payload, and the public key derived from the private key used to compute the DHT storage location and verify payload. So what the key we use in the DHT table is different from the ARID, but it's derived from the ARID. So anybody who has the ARID can derive that, but they still can't decrypt the message because the message itself is separately encoded in practice using GSDP. So we use the right one. Semantics are enforced by rejecting updates. So everybody, it's a consensus algorithm that you only pay attention to sequence number equal 1, even if the original owner of the private key chooses to publish a sequence number 2, the other clients won't pay attention to it. They'll ignore it. So then next, IPFS, the Interplanetary File System, which is the Distributed Content Address Storage Network. And the emphasis here is now on storage, not coordination, but we can use it as a coordination layer or a storage layer. Excuse me. It's an established network with consistent operation. It's well suited for coordination and signaling. There's at least 56,000 dedicated infrastructure nodes globally, but even there's vastly more than that come and go very commonly. The content persists reliably when pinned. So if you're running a server, you can pin content. Other than that, there's about a 48-hour DHT expiration. That basically is how long things can persist, a time to live before things get refreshed. It's basically a content addressable storage system. So files are identified by a content identifier, which is a cryptographic cache of the content, similar to how mainline DHT does it. That came too soon. Came to the wrong place. The two-layer storage model, however, it also has an immutable layer, as I mentioned, but it also has a mutable layer, just similar to mainline DHT. It's called the Interplanetary Name System that provides mutable pointers to CIDs. And we're using it for the same reason we use it in DHT, which is so that the key can be different from the value. It has a much larger size limit. The practical limit is 1 to 10 megabytes per item. And this is without asking permission, without setting up an account, without anything like that. You can just put objects, blobs, into this storage system worldwide, and it will at least keep it there for the length of time it would normally keep it there, even if you don't pin it. The content expires from the DHT about 48 hours, as I mentioned. And the IPNS record should be republished about every 4 hours. So that's basically that, and that's the mutable system that we work on. Kubo is the kind of standard implementation of the IPFS server. Long-term persistence requires pinning, which, as I mentioned before, and we do support that in Hubert. The latency is about 1 to 10 seconds for IPNS resolution, which is slower than mainline DHT. So there's a little bit of a trade-off there. You have to reuse the Kubo daemon or compatible IPFS node with the RPC API running. And again, we support write once semantics. Before publishing, we check to see if the IPNS name resolves. If it succeeds, then it's already published. So we basically return an error. If it fails, then that's actually good because then we can proceed with the publish. Unlike mainline DHT sequence number approach, we rely on the IPNS name existence check. Then we have the hybrid layer, which uses both the mainline DHT and IPFS. The hybrid storage combines mainline DHT and IPFS with automatic size-based routing. It chooses which layer to store the target blob in based on its size. If small envelopes, less than about 1,000 bytes, get stored directly in mainline DHT, and large envelopes have a two-step indirection process. We generate a new reference ARID for the actual envelope to be stored in IPFS. We store the actual envelope in IPFS at the reference ARID, and we store a small reference envelope in DHT at the original ARID. To retrieve this, we fetch the envelope from DHT. We check to see if it's a reference envelope. If it's a reference, we extract the reference ARID and fetch the actual envelope from IPFS. If it's not a reference, we return it directly. And this is entirely transparent to the callers. Fast retrieval of small messages with large capacity for big messages. And there's no size calculation required by the caller. In fact, the caller doesn't even care which layer it gets stored in when it's using the hybrid method. This requires that you be running a Kubo daemon, as well as use the embedded DHT client, which our Hubert binary already includes. The write once semantics are enforced separately by each backend. So the sequence number in DHT and the IPNS name check in the IPFS. In the current, if you download it today, there's a couple things still need to be implemented. We need to encrypt the reference envelope. Right now, the IPFS ARID is exposed, and obviously we store it in plain text, but that's something small that we have yet to implement, but that's coming very soon. And finally, we have the local storage layer or the SQLite storage layer, which is our centralized HTTP-based storage for testing and control deployments. It's a simple HTTP post API with write once semantics. It has put and get calls and has two potential storage backends. One is just an in-memory hash map, which is volatile and lost on restart, but we also support SQLite for persistent file-based storage. This includes direct array to envelope mapping. It's just a table, literally a key value table with the URs for the arids in the key column. We enforce write once. We also support time to live. So you can actually, if you're testing or whatever, and you want to support timeouts and time to live, you can specify that. We also clean up in the background once an entry expires. It's pruned automatically. And now we're ready for the demo. So I'm going to take a moment here and switch over to it. And you might have to do a little bit of editing here because this might be a moment to figure out how to stop the share here. Because Zoom loves to change things. And let's see.
Yeah, not yet.
Yeah, I know. I'm working on it. There we go. Stop share. Okay, now I'm going to share something different. Okay, you should now be seeing my Visual Studio Code window. And as you can see on the left-hand side, I have our stack of all the different crates we've released. Hubert is the one right here that we'll be working on primarily. Inside that, there is a docs folder with a CLI manual, and we'll be actually talking about the contents of that primarily. We also have the API manual because basically our Hubert crate can be incorporated as a library directly into your own Rust code, or it can be run as a CLI. And so you'll be seeing demonstrations of that. So the CLI manual starts out with our table of contents here. Goes over some of the material I've already talked about, basically shows you how to install Hubert directly from crates.io. You need to have the Rust toolchain installed. Shows you how to access help and the version number. And then we actually get into, we're going to scroll on here until we actually get into the actual main demos here. Now you can see I have a couple split windows here for other terminals. We'll be talking about those in a moment. But right now, I'm in the Hubert directory here, and I just want to show you that Hubert has a utility built into it to generate arids. We also have actually several of our tools generate arids because they're generally useful. As you can see, the arid in text form takes the form of a UR with the type arid, and then this is the actual encoded byte words that are the 32 random bytes. Ultimately, this is a CBOR or DCBOR object. So if we want, and I'll be actually running these commands in my own terminal down below. So actually by selecting these. So when I actually select these and press Control Enter, you'll see that it's actually executing these commands down here, and you can see this arid is different than this arid. You can always tell to glance whether two URs are the same because by just looking at the last 8 letters. Sometimes the last 1 or 2 letters will tell you if it's different because this is a CRC32 check. And so if those last 8 letters are different, there's only an astronomically small possibility that the two are actually representing the same object. In this case, they're obviously different. So this is, for example, what we're doing down here is actually alive. So the next thing we need to do is we want to create the value to store this. So this is the key that we're going to use to store into Hubert. We're going to now create the value, which is a UR envelope. Hubert also includes, since the size of an envelope matters, and because it's trivial to create very small envelopes using our envelope command line tool. Hubert actually has a built-in tool that lets you specify the number of bytes, random bytes in it. So we can actually use like our hybrid layer, which decides which layer to store it in. So in this case, I'm going to be generating a 20 byte envelope, and that's what that looks like. This just contains a byte string that's 20 bytes long. In this case, we're actually going to use, notice I didn't assign that to a shell variable. In this case, we're actually going to use a new envelope. We're going to compose this using our Gordian envelope command line tool. We're going to say envelope subject type string, which basically means the envelope will have a subject of type string, which is just this string, hello Hubert. We're going to echo that as the UR, and then we're also going to show its format. It will look something like that. So let's do that live. And so now we have, this is the UR of the envelope. This is the actual contents of the envelope in a human readable form. So now we're going to store that data. It's as simple as saying Hubert put arid envelope. And so each arid can only be written once, and attempting to write again will fail. So what's going to happen here is it's going to use mainline DHT. So it has to be less than 1,000 bytes. It will error if you give it larger than 1,000 bytes. I'm going to enhance this with one extra thing, which is I'm going to put the time command before it, which in the shell will basically start a stopwatch and tell us how long this takes. And it might take 30, 20 to 30 seconds to do its thing, but it's actually going out there. There you go. So as you can see, it took 6.6 seconds, and uh, and so therefore, if we have, for example, a different terminal, in, then we can say um, Hubert get arid. I'm also going to time this. And this retrieved that in 5.8 seconds. Um, and then of course it's the same envelope. So, and of course I can verify that even if I don't have it, but I can say envelope format, and then it'll show us that the actual contents of the envelope in human readable form. And of course you could use piping. So you can say Hubert get arid and then pipe that into envelope format, and that will work directly, or you can extract the string directly without the quotes. So you can say Hubert get arid envelope extract string, which extracts the subject of the envelope, which is this string. So you can use that directly without the quotes. And then, of course, sometimes you want to know whether backends are available. Hubert check is the command to do that. By default, we default to mainline. And so if you do that, it'll probably come back pretty quick and say mainline DHT is available. And then it just does a quick check to make sure you have network connectivity. If you don't, then that will fail because DHT is always available everywhere. Now, on the other hand, if you say Hubert check with storage IPFS, and you don't have your own Cubo server running, then you will get an error, as we just did. This is why I have this over here. So as you can see, we have this terminal here. I have the command IPFS daemon ready to go. This will start the local Cubo instance. And as you can see, it says it's listening on these ports, and it has a web UI. I'm going to copy this URL here. And then I'm going to open up the simple browser here, give it a URL, and you'll see this is actually running on my local system where I'm actually serving. I've already discovered 75 peers. I'm hosting 7 megabytes of my own data or data that's being chatted by the network. There's basically statistics here. We don't need to dwell on this, but I want to point out that I am running my own IPFS server right now. I'm contributing to and can access the IPFS network by doing this. Okay, so we'll set that aside. So now that when we do this again, it says IPFS is now available. Um, so you can also check to see if there's a storage, for example, like a server available at localhost with a particular port. And this is the default. So I'm actually going to start the local Hubert server as well. So this is our local server I mentioned with a local storage layer. Right now it's going to be running with in RAM. I'm not going to bother giving it a name for or specify this to use the MySQL table. So it says in-memory storage, and here's where it's listening, this is the port we've assigned to this 45678. So I can now check to see if that's running there. Oh, pasting it to the wrong terminal. There we go. There we go. So Hubert server is available. All right. So now you know how to check for the various backends availability. Obviously, it gives you errors if it's in the wrong port or host. So now we can actually continue with accessing Hubert directly. Now we're basically showing how Hubert puts and gets work with the mainline DHT, which we've already demonstrated, so I'll skip past that. And then basically the IPFS daemon we mentioned, and then the IPFS storage. And here you specify using the IPFS storage backend. So Hubert put storage IPFS, and then same thing, arid envelope. And I'm going to again do this. I'm going to time it. So we're using the same array we had before, but the arrays can be reused between them. There's no need to do that, generally speaking, but they are separate namespaces, the arrays between DHT and IPFS. There's no way of cross-checking between them. So generally you would actually generate a new array here, as I did. I skipped over that step. So you'll use fresh arrays every time, basically no matter what you do. This will take a little bit longer because it's actually going into the IPFS, and it's going through our server. Essentially, it's putting it up, and then it's basically chatting to the network, and it's basically waiting for it to be accepted by the network. It's important to note that the envelopes that we're storing actually get stored as binary blobs, even though you're seeing them as text URs. They actually literally get stored in these backend storages as binary blobs, not as text. So the text is just for your benefit and to make them easier to handle. But in both, because bytewords is not the most efficient way to store things. Like I said, it's designed to be easy to handle. But in the backends, we definitely use binary. So that took 48 seconds. And now we're just going to retrieve the same thing. We'll also time that. That was pretty much instantly, but then again, we did store on our own server here. So if this was on another node, then it would actually navigate the network to actually find the CID that was derived from the array we used. We also do support pinning. I won't actually do a demo of this right now, but you can generate an array and then say Hubert put with storage IPFS pin, and then you can also ask it for verbose output, and it will chat to you back the progress it makes of actually pinning the content. And this basically means that when you've pinned something locally, it will remain available globally until you unpin it. And therefore, you can basically use Hubert as a storage medium or for long-running coordination tasks that mainline DHT would be unsuitable for. So you can always use the IPFS command to list the CIDs that you've pinned, and you can also use it to unpin the content that you have. Notice that the content CID is given to you here in the verbose mode. It's actually chatted to you back as well. So when you actually say pin, it automatically writes back to you the CID. That way you can coordinate it with the IPFS command to unpin it. And hybrid storage essentially lets you do the same idea. So we have a small message here, envelope subject type string. This is a very small envelope. And we also have, and then we create the array for the small one, and then we put it. And then we're using the hybrid storage, array small message. And then you basically say, it says its size is less than 1,000 bytes. So it's doing the DHT, mainline DHT put. And then it's basically showing you how that finishes. Then we have a large message here where we're generating 2,000 bytes, and we have a separate array for that. And we put that, and as you can see, it decides that it's actually going to use IPFS. It's deriving a new array for that. It's putting it into the IPFS. The full envelope size is 2007 bytes, or 7 bytes of overhead there. Then it's getting the CID for IPFS. It's publishing it, and then it stores the reference envelope in DHT at the original array, as mentioned before. And so that's basically the process. And then it return. And so when you say get now, storage hybrid, array small or array large, this one was retrieved from DHT directly, and this one was retrieved from IPFS. So we've already talked about how the Hubert server, which I've actually, I'll just show quickly because it's pretty much instantaneous. So I'm going to generate an array, an envelope, put it and get it all in one step. And you see there it came back instantly because that's, we're running a local server. There's no time overhead. There's no multi-party coordination needed. You can store things with the time to live. This is set to expire after 3,000 seconds. I'm sorry, 3,600 seconds. You can, again, enable verbose logging to see what's going on. And then when you actually do a get, you can wait a certain amount of time. And this is important because in a distributed coordination scenario, one of the main ways, once you, and we'll show this in a moment, when you receive an array as part of a message, that whoever sent the array is going to be polling, waiting for you to give a response. And they may be polling several arrays at once, waiting for several responders to respond. But in this case, you're basically saying how long you want to poll, waiting for an ARID that you expect something to be at to become live. So I show the scenario where it times out. And then I read it a little bit more about pinning here. We don't need to go into that. The server time to live. Now, this is the last stage of the demo we're going to give here, which is how bidirectional communication works. And I've already alluded to it a number of times, but Alice wants Bob to sign a document. So Alice prepares the document. So Alice generates an ARID for the request and expected response. Now, we're not using GSTP here in this demo. We're only using plain text envelopes. GSTP builds on top of envelopes to provide sender authentication and recipient encryption. So right now, all we're going to do is generate the ARIDs for the request and the response. So we have those. Then Alice creates an envelope with the document and response ARID. So in practice, this would be encrypted. So the request envelope is envelope subject type string. This is the request. Please sign document.pdf. This could be the full PDF, even though we're just using a string here. And then we're going to add an assertion to it. Add assertion, predicate object string, response ARID, and the response. So this is basically, we'll show what this looks like in a moment here. We'll do all the steps right now. You see, so this is the request ARID. This is the response ARID. This is the response envelope in UR form, and this is the actual envelope formatted one where we have the subject, please sign document, and then a single assertion where we're giving the response ARID. This is an abbreviated version of the 32-byte ARID, just for human recognition here. Finally, Alice publishes the request. She says, Hubert put request ARID, press envelope, and we'll actually use mainline DHT to do this. So now it's putting this envelope again as plain text. And this is the binary version of this, which is not encrypted there. That took 6 seconds. And so Alice shares the request ARID with Bob. Now remember, this is something where I said that dead drops require some kind of out-of-band coordination. So you have to kick this off by, like for example, if Alice and Bob are both on Signal or can share a QR code or encrypted email, the ARID is never published. But in this case, Alice somehow conveys the initial ARID to Bob. Bob receives the request ARID, and all I'm doing here is a direct assignment from the request ARID to the received request ARID to simulate that. Then Bob retrieves the request. So Bob is now going to do a Hubert get on the received request ARID. And this is going out again to mainline DHT, retrieving the envelope, and this is going to show the formatted contents of it. So Bob has now retrieved that. And then this is the way we're going to extract. And I won't go into the mechanics of this. We've dealt with how to use our envelope tool, but it's finding the particular assertion, extracting the object, and then extracting that object as an ARID, and then it's showing it to us essentially. But this is the same response ARID that we had before that Alice had enclosed in that envelope. And then Bob creates his response. So Bob sends the signed document with the signature of that to Alice. He composes that, and then Bob publishes the response ARID. Now, in the meantime, Alice is polling maybe once a day, maybe once an hour, maybe once a minute for this. So Alice finally basically gets that so she's polling here, and there could be a timeout here, but she knows where to expect the response. So she gets that back. There we go. The signed document. This is just a signature of the document that Bob signed. So we've shown that ARIDs are only shared via secure channels. There's no direct communication needed between Alice and Bob, except the initial coordination of the initial ARID. But of course, this could take many terms, and it turns involve many different parties, as frost ceremonies do. Parties don't need to be online simultaneously. The storage network sees only encrypted envelopes. Write one semantics prevent tampering, and encryption and authentication using GSTP as an additional layer to this ensures confidentiality and integrity. And that is the end of the presentation.
Thank you, Wolf. Some quick commentary on this. Obviously, this is a proof of concept. Um, we wanted to demonstrate, I mean, obviously we could have done some of this just simply with a REST server, maybe added Tor to it. But I felt as we're really trying to demonstrate Exodus protocols, that we needed to go above and beyond a REST server with things like clubs and other kinds of coordination to really demonstrate the capability to be decentralized in a variety of ways, and demonstrating that we can do this with the mainline BitTorrent and with IPFS, and then in the future there could be other hybrid forms that allow for a wide variety of communication coordination opportunities. So that's why we've done this particular demo. Um, Obviously, I would, say anything at this stage, the point one stage, is pre-production. There are, I mean, besides the fact that we're using the command line, this code hasn't been, and our general approach has not been rigorously analyzed. We're also not doing things like perfect forward secrecy, or as I prefer to call it, future compromise resistant. But in principle, we've demonstrated that it can work. This is a suitable functional strategy for doing coordination, and kind of proves the general concept that we can use uh, these types of techniques with objects like clubs and ZIDs and other different kinds of things that need coordination, um, using really autonomous capabilities. Any other kind of you want to say as far as future work, Wolf?
Well, our next major phase of development in this case will actually be developing the multi-party frost signing protocols on top of Hubert. I expect will be one of our next major demonstrations, is actually showing a number of different processes actually kicking off and then completely autonomously coordinating a frost signing session and using Hubert as the substrate, as the coordination layer, and then showing that in real time. So I'm looking forward to giving that demo very soon.
Yeah. I mean, right now, the examples of Frost is that either the first party acts as a coordinator, or a trustless coordinator is selected. Um, but then that means all the participants in the Frost scenario need to communicate with that centralized coordinator, or the first party in the transaction, to do the operation. In this particular case, as long as we have pre-distributed the arids that allow us to be able to know that different kinds of events are happening, we can do so without ever directly connecting with each other at all in this. So I think that's a powerful demonstration that, as far as I know, nobody in the Frost community is doing with their servers. So we're hoping that this will be another opportunity for people to entree into our technology stack in useful and interesting ways.
Yeah, in terms of anonymized protocols, I can envision a lot of kind of innovative things where you can use a ratcheting protocol to periodically broadcast a new rendezvous point via an arid that is generated from something else, like every day or something like that, where even if it might expire, people who are in the field who have the initial secret can ratchet it forward, find the current one, and then start a communication through DHT or some other thing, very similar to how number stations work in the physical world. So there's all kinds of possibilities for interesting forms of swarming and distributed coordination with this kind of system.
Also, because of the nature of the arid, which is an apparently random number, and we do have to be careful that about that quality. There are a lot of things that are apparently random, so that means we can use things like adapter signatures as capabilities. We can do various kinds of ZK proofs or other kinds of multi-party communications, as long as, they're limited to the 32 bytes of an ARID, that can allow for other kinds of very interesting opportunities to increase privacy, improve coercion resistance, and in generally, solve problems in an Exodus protocol way.
Yep. Our BCR for ARIDS is basically makes it clear that ARIDS don't have to be random, but they have to be statistically random and they have to be globally unique. And there's lots of different ways of achieving that. And as Christopher just mentioned, so that does give rise to a lot of interesting possibilities.
Okay, well, thank you very much for the demo, Wolf.